Hello, and thank you for joining us. Today's webinar is LabVIEW Drivers for Control of Flow and Vacuum. Our presenters today are Doug Baker, Director of Sales and Business Development for Teledyne Hastings, and also Orestes Morales, Senior Test Engineer with Eagle Technologies. This webinar is being recorded and will be available within a couple of days. Okay, now I'm going to turn it over to our first presenter, Doug Baker.
Thank you, Shelley. Hello, and welcome to today's webinar entitled LabVIEW Drivers for Control of Flow and Vacuum. My name, as Shelley mentioned, is Doug Baker, and I'm honored to be joined today by Mr. Orestes Morales with Eagle Technologies. And before we get started, I want to mention that this webinar is being recorded. Also want to let you know that you'll be able to download the recording and the slide deck after this presentation. Also, both Orestes and myself really enjoy talking to folks about their applications. So if you have any questions or would like to tell us about your work, we look forward to hearing from you. Our contact information will be given in a couple of slides. Let's get started. After some quick introductions, we're going to describe LabVIEW and discuss why it's become so popular in the laboratory and in the factory for control, automation, and data collection and analysis. Next, as we begin to drill into LabVIEW, we're going to introduce the concept of an instrument driver. LabVIEW drivers are important because these are the software routines that are going to handle the data between devices. If you have a good library of drivers, then you have the building blocks to quickly create higher order LabVIEW routines to help you get your work done. After we've described LabVIEW drivers, we're going to talk about the benefits of using certified drivers. Now, certified drivers must meet certain guidelines. They're rigorously tested, checked by NI and the code developer before being released. Bottom line, certified drivers save you time and aggravation because you can be confident that the drivers have been tested and are going to work. Next, we will get to watch a LabVIEW Jedi Master at work, as Orestes is going to walk us through a demo of a system he created in LabVIEW using some of our instrumentation, using the certified drivers for Teledyne's mass flow controllers. And then to wrap up the webinar, we're going to tell you how you can download the certified drivers. And here's a spoiler alert. I'm going to mention it now that our certified LabVIEW drivers are free. And then lastly, we will tell you where you can go for more help on automation, flow, and vacuum instrumentation, or LabVIEW in general. As I mentioned at the top of the webinar, my name is Doug Baker, and I'm the Director of Sales and Business Development here at Teledyne Hastings, located in Hampton, Virginia. I started using National Instruments Lab Windows in graduate school as I worked on ultra-high vacuum experiments. Then when I started at Teledyne, started to use LabVIEW. Our engineering team uses LabVIEW for R&D testing, including collection and analysis of product compliance data. We also use LabVIEW routines developed in-house on several of our automated production calibration and test systems. But the real LabVIEW expert today on this webinar is Mr. Orestes Morales. Orestes is with Eagle Technologies. He has developed the suite of LabVIEW drivers for several of our instruments and has taken us through the entire certification process. Eagle has been super easy to work with, and it is my pleasure now to introduce Orestes.
Hello, everybody. As Doug mentioned, my name is Orestes Morales, and I am a Senior Test Engineer at Eagle Technologies. For more than 50 years, our company, with headquarters at Bridgman, Michigan, has provided turnkey systems seeking an all-in-one solution to automated production and testing challenges. We build custom machines that automate factories across the world. From high-tech robotics to advanced product testing capabilities, we offer end-to-end manufacturing solutions for every industry. We believe that if we're going to build machines to manufacture products, we should also be the one testing the products to be sure the final output meets the design requirements. Our testing systems go above and beyond standard implementation. To ensure this, we use advanced technologies like finite element analysis, dynamic MBH analysis, prototype engineering, additive manufacturing, and powerful software tools like LabVIEW, Testem, Power Controls, DISCOM, PLC development environments, and data collection software like Ignition. Our custom robotics and automated factory solutions can accomplish complicated tasks, from producing single components to reliably assembling them into a complete product. From filling pill bottles to constructing an Apple battery, there is no automation too large, too delicate, or too complex where it can help you accomplish your objectives.
Thanks, Orestes. And now just a few words about Teledyne Hastings. Our company is based in Virginia, USA. We design and build high quality, accurate, and rugged instrumentation for measuring and controlling gas flow and vacuum. In fact, our vacuum gauges are trusted around the world because of our reputation to be able to withstand the most demanding conditions, including over-the-road highway and rail applications, as well as laboratory and industrial environments. During the Apollo lunar missions, Teledyne vacuum sensors were selected to travel to the moon and back so that scientists could be confident that collected samples had been maintained under vacuum during return, re-entry, and splashdown. Our thermal mass flow meters and flow controllers are used in precision laboratory instrumentation and in challenging industrial applications. We have the infrastructure and flow standards to support high as well as low flow needs. Our largest flow controllers can handle flow rates up to 10,000 standard liters per minute. Flow meters, mounted on large laminar flow elements, can measure flow rates up to 15,000 standard liters per minute. Okay, so let's spend a little bit of time talking about LabVIEW, and we're going to address the question, why are we interested in this specific programming environment? Now, there are plenty of other approaches that are out there that will allow us to develop data acquisition and control routines. So what makes LabVIEW a good choice? Before I go any further, I don't want to sound like I'm a paid spokesperson for NI. I'm not. We don't sell LabVIEW or any NI products. As I mentioned earlier, our drivers are free. My goal is to simply make your implementation of our vacuum and flow products into your application, whether it be at a laboratory or a factory floor, make it as easy as possible. And we believe that in many cases, LabVIEW can help with that. Now, for one thing, LabVIEW allows you to easily connect a wide variety of devices. In addition to our sensors, controllers, and power supplies, LabVIEW can work with many different digital multimeters, signal analyzers, oscilloscopes, valve positioners, imaging systems, the list goes on and on. And all of these things working in the LabVIEW environment allow the user to automate testing. So not only is LabVIEW useful in R&D, but it's also very powerful when it comes to manufacturing, as it can help lower cost and improve reliability. One of the most attractive aspects of working in LabVIEW is that it's easy to learn. With just a few lessons, you can be up and running with the basics. And once you have some programming skill, you can quickly design and test code. This is great for R&D efforts where experimentation may lead to desired changes in data collection sequences, or you may decide that you need to completely change which physical parameters are needed to collect and analyze. And finally, NI offers excellent support with courses, user groups, discussion forums, and of course, a large library of available device drivers. So now that we've touched on why we're going to use LabVIEW, Orestes is going to talk about what is LabVIEW.
LabVIEW is a system engineering software that offers a graphical programming approach that helps you visualize every aspect of your application, including hardware configuration, measurement data, and debugging. This visualization makes it simple to integrate measurement hardware from any vendor, represent complex logic on the diagram, develop data analysis algorithm, and design custom engineering user interfaces. LabVIEW programs or subroutines are called virtual instruments or VIs. Each VI has three components: a block diagram, a front panel, and a connector pane. This last one is used to represent the VI in the block diagram of other calling VIs. The front panel contains controls and indicators. Controls are inputs that allow a user to supply information to the VI, while indicators are outputs that display the results based on the inputs given. The back panel, which is a block diagram, contains the graphical source code. All objects placed on the front panel will appear as well on the back panel as terminals. The back panel also contains structures and functions which perform operations on controls and provide data to indicators. Collectively, controls, indicators, structures, and functions are referred to as nodes. The structure of the graphical block diagram, in which the developer connects different function nodes by drawing wires, defines the execution flow. These wires propagate variables, and any node can execute as soon as all its inputs have available data. A virtual instrument can be run as a program, with the front panel serving as a user interface, or as a function when dropped onto the block diagram. For this last case, the front panel defines the inputs and outputs for the node through the connector pane. This means that most VIs can be easily tested before being embedded as a subroutine into a larger program. LabVIEW graphical approach allows non-programmers to build programs by dragging and dropping virtual representations of lab equipment with which they are already familiar. The programming environment with the included examples and documentation make it simple to create small applications. This is a benefit on one side, but there is also a certain danger of underestimating the expertise needed for high-quality code programming. For complex algorithms or large-scale code, a programmer must possess extensive knowledge of the special LabVIEW syntax and the topology of its memory management, especially if he or she doesn't want to end with a very well-known spaghetti code problem. LabVIEW can control devices and receive responses from them. To perform this, an interface that enables LabVIEW to connect to the device or instrument is required. These interfaces are called LabVIEW Drivers, and there is a vast library of them available within the LabVIEW ecosystem. Some drivers are developed by NI, while others might be developed by the manufacturers or third parties. An instrument driver provides the interface between the core LabVIEW software and the instrument or device that needs to be controlled or monitored. The LabVIEW instrument driver is, essentially, a set of software routines that facilitate data exchange with the instrument or device. Within the overall driver, there are individual functions that perform specific tasks. For example, configuring the device, reading from, writing to, and triggering the device or instrument. Instrument drivers simplify instrument control and reduce LabVIEW program development time by eliminating the need to learn the programming protocol for each instrument. A LabVIEW driver converts the use commands in LabVIEW into instructions required for that device and sends them through a communication protocol like USB, serial, Wi-Fi, Ethernet, GPIB, to cite some examples. Some LabVIEW drivers might incorporate all possible functions to control the device over different communication protocols, while others might have a limited set of instructions or capabilities. Although many are available free of charge, sometimes there might be costs associated with them. It will finally depend upon the devices, the manufacturers, and the developers of the code. Locally, most of them are available within the LabVIEW ecosystem, adding value without additional charge. Using a standard architecture for all LabVIEW instrument drivers has several benefits. It improves the consistency of instrument drivers for the benefit of end users and the quality of the drivers, minimizes duplicated effort, improves ease of use for end users by providing a consistent methodology for using instrument drivers from different sources, and streamlines the instrument driver development process for the benefit of instrument driver developers. Many programmable instruments have a large number of functions and modes. With this complexity, it is necessary to provide a consistent design model that aids both instrument driver developers as well as end users who develop instrument control applications. The LabVIEW plug-and-play instrument driver model contains guidelines that define how the instrument driver interfaces with the user and other software components in the system. The figure shown illustrates how the instrument driver interacts with the rest of the system through an interactive interface and a programming interface. The application programming interface, or API, is the set of user-callable instrument drivers VIs used in end-user systems. For example, a manufacturer test system might make instrument driver calls to communicate with a multimeter or an oscilloscope. The end user learns about the API through the instrument driver front panels. By interactively running the front panels of the instrument driver VIs, end users understand how each control affects the instrument. After the end users understand the settings, they will be capable of incorporating the instrument driver VIs in their application. The virtual instrument software architecture interface is the set of LabVIEW functions the driver uses to communicate with the instrument hardware. VISA is an established standard instrumentation interface that controls GPIB, USB, serial, and other instrument buses. Support VIs are VIs that you don't intend the end user to access directly. Therefore, support VIs are not part of the instrument driver API. For example, instrument drivers often call the default setup VI during initialization to set the instrument in a state that allows for a robust instrument control by the rest of the instrument driver VIs. Only the initialize and the reset VIs use the default setup VIs as sub-VIs, so it is considered a support VI. Certified LabVIEW drivers follow all the mentioned design guidelines and are rigorously checked by NI and the driver developer before being released. The setup proposed today for the demo consists of a THCD401 display processor and 4 300 series flow meters. From left to right, the front panel of this virtual instrument shows a mass flow chart that includes the signals coming from each of the mass flow meters. The flow control section diagram shows how the pump, flow meters, and tubing are connected. When a mass flow valve is closed, the corresponding representation will turn red, and when the valve is open or in auto mode, it will stay green. Tubing will be highlighted in blue if there is a possible air pathway from the pump to an exhaust. At every corner of the flow control diagram, we have an indicator that shows the current flow value of one of the flow meters and consoles to set up the valve mode and the set point. The mass flow meter connected at channel 4 regulates the airflow intake that comes from the pump, while the other mass flow meters regulate the output flow. Finally, on the right upper side of the front panel, we have a live video stream of the setup and below some settings and execution controls. Before running the VI, we will first check that the right visa resource is selected. For this case, we are using a USB serial connection, but it is possible to control the THCD401 via TCP/IP2. Let's start the program. As you can see, all indicators get updated with incoming data. Now we can play with the controls. For example, let's set the mass flow meter number 4 to auto mode and a set point of 100 SCCM. Because all other valve set points are 0, there's no sustained airflow from meter number 4. Let's set a 50 SCCM set point for meter number 3 and 25 SCCM to meter number 1 and meter number 2. Now we can see how the mass flow values reported by each sensor changes in the chart and the diagram. Let's fully close meter number 1. As we can see, the overall flow got reduced to 75 SCCM, which is the total mass flow output between meter number 2 and meter number 3. We can also zero each of the sensors programmatically. For example, let's close flow meter 4 and execute the zero command on the other 3 sensors. After a brief delay, we will see that the numbers shown are closer to 0 in the front panel indicators and the THCD401 screen. Now, let's take a look at the block diagram. Since this application is for demo purposes only and it is not time sensitive, we use a simple event handler design pattern. The execution flows start by initializing the connection with the device. If the connection fails, an error will propagate through the while loop and event handler structures, stopping them and then prompting an error message. If the connection is successful, the event handler will wait for user events and time out every 100 milliseconds. During the timeout, the output current reading, set point values, and set point mode VIs are read, and the mass flow chart, flow diagram, and other controls and indicators get updated. When the user changes a control's value or presses a button, an event is registered and a specific code gets executed. For example, we can observe that when the mass flow meter 4 set point value is changed, the new value registered by the event handler structure is passed to the set point value VI and then updated in the device. We use the new valve parameter instead of the corresponding control to avoid a race condition because we use that same node as an indicator through a local variable. Although out of the reach of our demo, we also have a parallel loop that runs the NI Vision Acquisition Assistant to provide the video stream and a stream channel writer reader to share the value of the stop variable among both loops. When the stop button gets pressed, an event is triggered, stopping both while loops and executing the closed connection VI. If there was an error during any part of the code, the simple error handler VI should show a prompt on the screen for user acknowledgement. To summarize, in this demo, we show how easily we interacted with several mass flow meters using the new certified THCD 401 LabVIEW driver. When using devices like the THCD display processors, the 300 series flow meters, or the HVG vacuum pressure gauges, these new LabVIEW drivers will help you save time, money, and effort during the development process. The setup proposed today for the demo consists of a THCD 401.
Thank you, Orestes. Now that we have seen what these drivers can do, I will tell you that all of our certified drivers are posted on NI's Instrument Driver Network, or what NI calls their ID net. You can find this by going to ni.com and hovering over support, and next clicking on software downloads. From there, you can click on third-party drivers and search for Teledyne. Of course, it's a much simpler path. You can just Google Teledyne Flow LabVIEW Drivers or Teledyne Vacuum LabVIEW Drivers. If you run into any trouble, you can contact me at dbaker@teledyne.com, and I'll be happy to send you a link so you can download the driver you want. So today, Orestes demonstrated some of our flow products by using and controlling 4 digital 300 mass flow instruments, or what we call 300 views, through the new THCD 401 display processor. Of course, we could have done the demo setup without the THCD 401. Nonetheless, its main advantage is that with the THCD 401 4-channel power supply, you have centralized control over all the sensors and fewer cables to connect. There's also a meter only version of the digital 300. Now, in the picture on the right, we're showing our IP67. That's a waterproof model of the digital 300. This model is great for outdoor or splashdown areas. All digital 300 feature excellent accuracy with the accuracy specification of 0.5% a point plus 0.2% of full scale, which gives the user the benefit of tighter process control. And as you saw in the demo, the digital 300 can be configured with a local color touchscreen display. The benefit with this version is that you can get up and running very quickly. So I like to say if you can get money out of an ATM, then you can control flow using a digital 300. Our HVG 2020 vacuum gauge, shown on the left, can also be configured with or without a touchscreen display. The A version of the HVG 2020 uses an accurate piezoresistive sensor to measure vacuum from 1 atmosphere down to below 1 torr. And the HVG 2020B features 2 sensors to provide the user with a broad range of accurate vacuum measurement from atmosphere to less than 1 millitorr. Now, both flow and vacuum lines feature analog and digital outputs, so they're each very flexible, easy to set up, easy to use, and that's going to save you time. And we're also proud to announce the release of our latest certified drivers. Eagle Technologies has produced certified LabVIEW drivers for our single-channel THCD 101 power supply controller. So the 101 can provide 24-volt or plus minus 15-volt to power flow meters, flow controllers, vacuum gauges, or various other sensors. The single-channel THCD 101 accepts linear analog signals and will display readings with units on its bright display. And 5-volt analog command signal to operate our analog models of mass flow controllers. The 101 also has set point relays, which are great for process control. And in addition to a USB connection on the rear, the THCD 101 has an Ethernet port with an internal web server, and that allows the user to quickly configure and control the instrument. Of course, when you order from us, we're going to go ahead and set up the THCD 101 according to your instructions. So you can simply open the box, attach your device, power up, and get up and running. So the THCD 101 is a single channel version, and we also have the 4-channel version called the THCD 401. That's what Orestes used in the demo. Both the 101 and 401 can operate as standalone instruments or through LabVIEW, or can be operated with our free Display X Windows software. And now one quick slide on where you can go for help. If you're interested in factory automation, whether for manufacturing or testing, feel free to reach out to the team at Eagle Technologies. Restus is standing by to help you get started. And I'm always available for any questions you have about vacuum or flow applications, especially as it relates to measurement and control. And I also want to mention that Teledyne Hastings has a very strong global network of technical and sales channel partners that are willing to help you wherever you are. As far as learning LabVIEW, you can start with the ni.com website. They have many training modules that are free, and they also have a separate website called learn.ni.com, which has tons of topics. And I often find that YouTube is a good resource when just starting out. And ni.com also hosts forums where you can post questions. And if you want to get more serious, there are LabVIEW, what they call core courses. Those start at like $500. As Orestes mentioned earlier, the LabVIEW environment makes it easy to create small applications, but for high quality programming of complicated algorithms, it's better when a programmer possesses some knowledge of LabVIEW syntax and memory management, so you don't wind up with what Orestes called spaghetti code. But again, you can get started controlling vacuum and/or flow applications using our certified drivers. Using these drivers is a first step towards good programming and in turn, reliable process control. And as mentioned earlier, we welcome your questions. I can be reached at dbaker@teledyne.com, or you can contact Orestes at o.morales@eagletechnologies.com. I want to thank you again for joining us today. And as a reminder, there is a recording of this presentation. It's going to be posted for you along with copies of the slides. I also want to thank Orestes for his excellent work, both with the development of the certified drivers and with the demo he's shown today. One last note, our entire library of previous webinars can be found in the resource center of our website. And our website address is www.teledyne-hi.com. Thanks again, and have a great day.